We have had a quick look at one method of solving a non-homogeneous linear ordinary differential equation with constant coefficient of order greater than 1. What was that method called? It was called the method of variation of constants or method of variation of parameters. It's a method which is not mentioned in many books, and that's why I spent some time on it. Also, it is useful to be aware of a number of different methods that can be used. One should not restrict oneself to using only one particular method for solving any kind of problem. We are going to take a look at the method of Laplace transformation, but depending on the problem, you may find some of the alternative methods also good or even better. And so one should be aware of a number of methods of solving problems like this. So before I get on to the method of Laplace transformation, I'll spend some time talking about one more method, which again is not normally mentioned in most of the textbooks, but which is also quite simple to understand, and it can actually be used without much difficulty. We saw that in order to solve the first order differential equation, whether homogeneous or not, was not very difficult. The homogeneous equation was of course very easy to solve because we knew the exponential function would work. The non-homogeneous equation that we solved with the help of the method of variation of parameters is when the degree of the equation is more than 1, for example the equation of degree 2, 3 and so on, that there is something more to be done. And we saw that if you had the equation which was of second degree, then we had to look at a polynomial associated with the polynomial differential operator, and this particular equation was called an indicial equation. And then we had to solve the problem of finding this m, or in other words finding the roots or zeros of the polynomial. And then one has to use appropriate exponentials and so on. But we can do things a little differently using this idea of a polynomial, all right, but instead of finding the roots, say m1, m2 etc., depending on the degree, and then saying that e raised to m1t, e raised to m2t and functions like this will build up our solution, one can look at it in the following way. Instead of roots of the polynomial, one could talk about factorizing the polynomial. In fact, that's how we really learn polynomials in school. Most of us have learned first the idea of factorization of a polynomial than the idea of a root or a zero of a polynomial. For example, all of us have learned this particular factorization: x squared minus y squared equal to x plus y multiplied by x minus y. Looks very simple, but many of us have had difficulty in understanding it and in remembering it in school, and there are many who just cannot remember it and therefore have to leave mathematics or algebra at least. Now this idea of factorization of a polynomial can be used as follows, and let me first take a numerical example, that is an example where there will be some particular numbers, and I have written down this equation earlier as an example. Suppose I write d square plus 5d plus 6 operating on x equal to 0. This is the homogeneous equation that I want to solve. Then because this d square plus 5d plus 6 is a polynomial, of course it's in d, not in the familiar x, I can think of factorizing it. Factorization of the polynomial of course requires finding the roots, but the emphasis is not on the roots as such, the emphasis is on the factors. So what is a factorization of this? Of course I have chosen the numbers which are so nice that with a little bit of effort you can find out the factorization without even finding the roots. For example, d plus 2 into d plus 3 is a factorization of this polynomial. As you can check, I get d square plus 2d plus 3d, so that's 5d, plus 2 times 3, that's 6. So this polynomial d square plus 5d plus 6 operating on x factorizes into d plus 2 into d plus 3 operating on x, so that equal to 0. That's the homogeneous equation that I have to solve. Of course, I could have written the factors in the other order, d plus 3 into d plus 2 x equal to 0. Now there is a difference between a factorization like x square minus y square equals x plus y into x minus y, where x and y are supposed to be representing numbers. Here d square plus 5d plus 6, here d is not going to be replaced by a number because d is an operator. D represents the operation of differentiation. So then what do we mean by factorization? Into d plus 2 into d plus 3, or what is meant by saying that d square plus 5d plus 6 is d plus 2 into d plus 3. Now what is meant is very similar to what is meant by d square. What did d square mean? Did it mean that some number d was being squared? No. D squared is not like 5 squared, where 5 squared is simply 5 into 5, so carry out the arithmetic and get the product. So what was d square? Why did I introduce d square? Because I had d square x by dt square. This was the traditional way of writing the second derivative, but even there I see this d square and dt square. So am I squaring d and am I squaring t? No. What this means is I am applying the differentiation operation twice in succession. I start with x, find its derivative, find the derivative of that derivative. So it's d operator applied in succession, or d followed by d. So if that's what d square means, then what is the meaning? So d square means d followed by d. Apply d to it, whatever x, apply d to the result. That's what d square means. If that is the case, then what is d plus 2 bracket followed by d plus 3 x? What this means is 2x, apply d plus 3 first, apply the operator d plus 3 first, which means what? Calculate dx plus 3x. To that result, you apply the operator d plus 2, and the whole final result should be equal to 0. This is the problem of the homogeneous equation. I am looking for a function x such that when I apply the d plus 3 operator to it, that is when I calculate d of x plus 3x, and then to that result, let's call that result y, I apply the operation d plus 2, therefore I find out dy, that is the derivative of y, and add to it 2y, the whole result should turn out to be 0. Find me such a function x. That's the problem. Now what has this factorization done? Now if you have been attentive, you can see that from this I get a method of solving the original equation d square plus 5d plus 6 acting on x equals 0. Because as I have written here, d plus 3 acting on x, if I represent that by y, if I denote it by y, then what I have here is d plus 2y equal to 0. Now of course I didn't know x, I wanted to find x, but I don't know y also. So what's the difference? The difference is now this y satisfies a first order homogeneous differential equation, and we already learned how to solve it. We already know how to solve a first order homogeneous equation. How do I solve it? The solution involves the exponential, and what else? It involves the initial value. It involves the initial value y at 0. But y is d plus 3x. So what is y at 0? Because y is d plus 3x, it is just another symbol or a name for d plus 3x. So y 0 is simply the derivative of x at 0 plus 3 times x 0. So if I know x 0 and if I know the derivative of x at 0, then I know y 0. Once I know y 0, I can solve the homogeneous equation d plus 2y equal to 0, find out what y of t is, but I am interested in x. So how do I get my x? But what was the relationship between x and y? Y was just another name for d plus 3x. So now I have the second equation, d plus 3x equal to y. Now this is not a homogeneous equation, it's a non-homogeneous equation, but it's a non-homogeneous equation of first order, and we know already how to solve it. So to solve the second order homogeneous equation, what I end up doing is I end up solving two first order equations. I solve one particular first order equation, get its solution, then that solution becomes the forcing function or the input for the next differential equation to be solved of first order, and that gives me the solution that I am looking for, the function that I am looking for. Now what we can do for a second order differential equation, we can certainly do for a third order differential equation, provided we know how to factorize the polynomial into three first order factors or first degree factors. Now that's what one has been talking about in school, factorizing of polynomials, and subsequently when one talks about finding the roots of a polynomial, then that amounts to doing the same thing. That is, once we know the roots of the polynomial, we know the factors. And when we talk about repeated roots, what you really mean is repeated factors. So for example, if I write down, and I wrote this earlier, I had say d plus 3 cube equal to acting on x equal to 0, that was the third order differential equation. For that, the indicial equation was m plus 3 cube equal to 0, and for this, no matter how clever I am, I can only get one root, namely m equal to minus 3. But then why do I talk about three roots? Why don't I say that there is only one root? Why do I say that there are three coincident roots, or there is a root minus 3 rather of multiplicity 3, or there is a repeated root repeated 3 times? What really we mean is that in the polynomial, the factor that corresponds to the root is repeated 3 times, which it is. M plus 3 is the factor, but the polynomial is not m plus 3. The polynomial is m plus 3 multiplying m plus 3 multiplying m plus 3. So the factor m plus 3 appears 3 times, and therefore we say that the root minus 3 is of multiplicity 3, or is a repeated root repeated 3 times. So that talk about repeated root idea really refers to factors anyway. Now of course we just have to be careful here. If the factors are m plus 3, then the root is minus 3. So the number that appears here appears as plus 3, the root is minus 3, because the root is what makes this 0, and m plus 3 is 0 when m is minus 3. Now in a hurry, I have seen students making this mistake, that they factorize all right, but when they are asked to find out the root, because that will be needed later on in what is called the root locus method, they will take the root for this polynomial m plus 3 cube as not minus 3 but 3. Now that's kind of a mistake, should not take place, and one should be careful. But these are some things which one has to be careful about. If you mean 2, you should not write minus 2, or if you mean minus 2, you should not write plus 2. It's as simple as that. And so we have an alternative method, namely factorize the polynomial differential operator into linear factors, first degree factors, and then solve first order differential equations successively. This is a method which is quite simple, and it can actually be used for solving lower order differential equations by hand. That is, suppose you are asked to solve a fourth order differential equation, then as I told you, no matter what you do, whether you use Laplace transforms, or you use the earlier method, or you use this method, you have to find out the roots of a polynomial. Once you have the roots of a polynomial, factorizing the polynomial is immediate, and so you can use that method. In fact, we will see that when we use the Laplace transformation method, we end up factorizing polynomials also. So it's not that factorization of polynomials is a very low grade method or anything like that. It is involved in the Laplace transformation method of solution also. There is only a little bit of a problem here, and that is again a problem which we have come across earlier. When we looked at roots of a polynomial, I said that there are 3 or 4 cases, and in one of those cases the roots happen to be complex, or as a fourth case purely imaginary. So much as you may not like them, you end up using complex numbers. Now again, in electrical engineering, if you want to study any part of it, the use of complex numbers today is almost unavoidable. And so that's a concept which is very useful, and therefore one already becomes familiar with it in mathematics. When you learnt your mathematics, you learned what may be called theory of functions of a complex variable or complex numbers and their properties and algebra and so on and so forth. You may not have realized where is all of this going to be used. Well, it is definitely very much going to be used in electrical engineering. Perhaps in your circuits, network theory, machines course, you have already made use of complex numbers. The complex numbers, not only complex numbers, but their geometrical representation as what are called phasors or even vectors, and sometimes they are called rotating vectors to distinguish them from quantities like force or velocity, which are true physical vectors. So complex numbers we can't shy away from, and therefore roots of a polynomial may be complex. Well, that's fine. And of course, thanks to a formula which goes back to Euler, one can go from complex to real and real to complex without too much of a problem. And this is something again which one has to learn in electrical engineering, and today's students are lucky because your calculator has this provision, so you don't have to really think much about it. What is it that I am referring to? Problems like this. A complex number is given in this form, let's say 2 plus j3, or in mathematics it will be probably written as 2 plus 3i. Change this into the so-called polar form, that is some positive number and some angle. Or going back to Euler, then this 2 plus j3 would be represented by some coefficient a, which is a positive number, multiplied by e raised to j theta, where this a is the modulus of the complex number and theta is the argument of the complex number. And this is called the rectangular to polar conversion. From the rectangular form 2 plus j3 obtain the polar form, and conversely from the polar form go to the rectangular form. Now this is a function which is provided on most modern calculators, pocket calculators. In my time we had to do it using slide rule and doing squares and addition, square root and whatnot, and looking up sine or sine inverse on the slide rule, or using trigonometric tables. Today it's all done for you, but you have to know how to do it. So make yourself familiar with this conversion from rectangular to polar and polar to rectangular form of complex numbers. So if we are not afraid of complex numbers, then we can look at factors, linear factors, which have complex numbers in them. Let's take the example which I had taken earlier, though I did not write down the polynomial. Let's say I have d square plus 2d plus 2 is the operator. So my differential equation is, let's say, d square plus 2d plus 2 acting on x equals the function 0. Find x. This leads to the initial equation m square plus 2m plus 2 equal to 0, and the roots of this turn out to be complex. They are minus 1 plus or minus j into 1, or minus 1 plus minus j. And if you remember, I had shown them in the complex plane as a pair of crosses like this, and I wrote here minus 1 plus j1 and minus 1 minus j1. The horizontal axis usually is called the real axis, the vertical axis is called the imaginary axis. So this is a plot which shows the roots of this complex, of this polynomial of degree 2, but the roots are complex. Now if the roots are complex, when I factorize it, the factors also will have complex numbers in them. And so what will be the factorization? The factorization will be d plus 1 plus j and d plus 1 minus j. And you can check that these two, when multiplied out, do give you d square plus 2d plus 2. So now I have complex numbers inside the factor. So corresponding to this factor, then the root is minus 1 minus j, and corresponding to this factor, the root is minus 1 plus j. But I need not be afraid of it. In place of a real number that I had earlier, say d plus 2 into d plus 3, I have now complex numbers. So this x equal to 0, I have to solve it. Fortunately, as electrical engineers, we not only live with complex numbers, but we live with something more complex than that. We look at expressions like e raised to j theta. and of course everybody knows what is e raised to j theta. E raised to j theta is cos theta plus j sin theta. And this relationship is usually ascribed to Euler, so it goes back to 230 years nearly. Of course, Euler was a great mathematician, we are not, but we need not be afraid of using this relationship. So using this relationship, then when I write e raised to mt, if m is not real but it is complex, then what does it mean? Well, suppose m I replace by what I have here, say minus 1 plus j, so it is e raised to m is minus 1 plus j multiplied by t. Now this can be written as e raised to, separating this into minus t plus jt. Now again, therefore this is e raised to minus t multiplied by e raised to jt by the law of index or exponents, and therefore this is equal to e raised to minus t. Now I go back and expand e raised to jt as cosine t plus j sin t. So this whole thing then is e raised to minus t cos t plus j e raised to minus t sin t. So this exponential e raised to mt, when m is complex, turns out to be not real but complex. It has a real part and it has an imaginary part. Now fortunately what happens is that when you solve the equation, you just don't have this particular m only, because I had two factors, and in one of the factors I had 1 plus j, in the other factor I had 1 minus j. So when you actually solve this equation, carry on the computations, you will find that in the end the answer will be real. There won't be any j remaining in your answer. In fact, if it remains, then you have made a mistake somewhere. So although we will work with complex numbers and complex functions, at the end of it, when we get to the final solution, you will find that the solution has only real terms, and the terms are of this kind: e raised to minus t cos t, e raised to minus t sin t. Now one should know the graph of these functions. Electrical engineers should know what the graph of these two functions look like. And what are they called? Because there is this e raised to minus t, so it goes to 0 as t increases. Goes to 0 meaning limit as t increases is 0. Within 5 time constants it will be something like 1% or 0.01. That's e raised to minus t, is the exponential decay. But that is not sitting by itself, that is multiplying cosine t. If I had only cosine t, or if I had only sin t, then what is it that I have? I have a simple sustained sinusoidal oscillation, and the frequency, the angular frequency for it will be simply omega equal to 1, because it is cos t not cos omega t, omega equal to 1, and therefore a corresponding frequency 2 pi f equal to 1, so f equal to 1 by 2 pi hertz. But I don't have that, I have that multiplied by e raised to minus t. So this is said to be a sinusoidal function, either cosine or sine, the common name for it is sinusoidal function, which is exponentially damped. So it looks, now I would like you to draw the graph of these two functions, e raised to minus t cos t and e raised to minus t sin t, carefully by using your graph paper, by choosing the appropriate scale on the time axis, choosing the appropriate scale on the value axis where you are going to plot the value of this function. For example, put t equal to 1, use your calculator to find out what e raised to minus t cosine t is. Maybe you should choose t equal to 0.5 also. So choose a number of values for t, calculate this expression e raised to minus t cosine t, get enough number of points and then join them by a smooth curve and see what it looks like. What it will look like, I will show you the drawn figure. In fact, most of your books, textbooks on control theory and on circuit theory will have plots of these functions. It's not enough to just see it in the book, you should be able to plot it yourself. So let me do it, but Suppose I want to plot cosine t, then how do I start? First I put two lines here, 1.0 minus 1.0, because I know that cosine t lies between 1.0 and minus 1.0. It takes both the values, of course. It takes the value 1 at t equal to 0, t equal to 2 pi, t equal to 4 pi, and so on. It takes the value minus 1 at t equal to pi, t equal to 3 pi, and so on. So on the horizontal axis I will put here pi, 2 pi. In fact, I will put pi by 2 for a reason you will see. So this is pi, this is 3 pi by 2, and this is 2 pi. So if I plotted only the cosine curve, what would it look like? It will be 1 here, it will be 0 here, it will be minus 1 here, it will be 0 here, and again it will be 1 here. So its graph will look something like this. As engineers, we have to be good at drawing. We need not be very good. We are not going to be artists, but we have to be reasonably good at drawing. As I told you, my exponential graph should not look like what it should not look like. It should not have corners. It should not behave in some arbitrary way. No, that's not acceptable. Similarly, the cosine graph should not be just drawn carelessly. I'm not saying that my graph is exact here, but at least some salient points are there. It is 1 at 0, 0 at pi by 2, minus 1 at pi, 0 at 3 pi by 2, and back again to 1 at 2 pi. So what have I done? I have put two lines, minus 1 and plus 1, and I made them reasonably equal distance from the x-axis or t-axis. On the t-axis I have put down 4 points, pi by 2, pi, 3 pi by 2, 2 pi. Again I have been a little careful. I have not been absolutely careless. The distances are not exactly equal. I have not even measured them. I don't have a graph paper, but I have not been careless either. And then I am drawing a smooth curve, and smooth meaning when one knows that here, for example, it's sort of rounded off like this. Similarly, it begins with a slope which is 0. It ends with a slope which is 0. These are some of the things which, as electrical engineers and as control engineers, you must become not only familiar but also reasonably skilled at. Now this is only the plot of cosine t. So this is cos t. But this is going to be multiplied by e raised to minus t. So what's going to happen? At t equal to 0, e raised to minus t is 1. So this is just what the product is. But by the time t becomes pi by 2, I have e raised to minus pi by 2. Now e raised to minus pi by 2 is already less than e raised to minus 1, which is about 0.37. But of course this is going through 0, so there is no problem. But at the next point where the function takes its maximum absolute value minus 1, cos t is minus 1, but e to the minus t now is e to the minus pi. That's more than the exponent is larger than minus 3. So it is less than e raised to minus 3. Now e raised to minus 3 may be of the order of say 1 by 20. So the value of the function will not be minus 1, but it will be 1/20th of it. By the time I go to 2 pi, cos t is again 1, but e raised to minus t is now e raised to minus 2 pi. So it's even less. So it's going to go through 0 here, it will start decreasing, then here it is already much less, it will go through 0 again, here it is much less, and so on. So if I were to show more than one period of the cosine function, and now because I don't have the time, I don't want to spend the time actually drawing it, it will look something like this. It will have oscillations. The oscillations are because of the cosine, but the values will go on decreasing because of e raised to minus t, the damping or the decay. So it will look as a very quick graph, something like this. Exponentially decaying sinusoidal function, that's the name given to it. And in control theory, this is a function you come across. You cannot avoid it altogether. You not only have the exponential function, you not only have the trigonometric functions sine and cosine, you also have exponentially decaying sinusoidal functions. Not only that, we came across something else earlier. We had a function like t e raised to mt. In particular, we could have t e raised to minus t. If it was t, then it is something which is going to grow without limit. If it was e raised to minus t, it is going to decay to 0 as t tends to infinity. What happens to the product? T into e raised to minus t. So this is another homework. Plot the graph of t into e raised to minus t by choosing a number of different values of t. Plot it on a graph paper using appropriate scales for the horizontal and for the vertical axis, and check for yourself what this plot is going to look like. It's quite different from this exponentially decaying sinusoidal function, because e raised to minus t has no oscillations, t has no oscillations. Yet it shows something, it shows one oscillation at least, because at t equal to 0 it is 0, although e to the minus t is 1. So this is an exercise which you must carry out, because again this function and sometimes t square into e raised to minus t also may be needed. One should know at least qualitatively what this behaves like. Okay, so solving higher order LDAWCC with initial conditions is not that difficult. Perhaps we have found out one more method of solving such a differential equation, namely the method of factorization of the polynomial differential operator. You can go back to your mathematics course or a mathematics textbook which asks you to solve some specific simple looking linear differential equations maybe of second degree or third degree with some simple forcing functions like sine t or cosine t or e to the minus 3t on the right hand side, or just unit step, that means 1 on the right hand side, and solve them using the two methods that I have mentioned so far. The method which uses the complementary function or the general solution of the homogeneous equation, and then from that also getting what is called the impulse response, calculates the zero state solution or the solution that depends on the input, and then adds up the two. That's one method. The second was factorization method. And now we are ready to start taking a look at the third method, namely the method of Laplace transformation. Once again, this is a method which every control engineering person, whether from electrical engineering or instrumentation engineering or mechanical or chemical, today it's almost imperative. By the way, you have of course a lot of program packages, a lot of software which is available, which will do a lot of work which earlier we had to do by hand or by using the pocket calculator or the slide rule even, or even a computer, but writing down equations, substituting, and then adding, subtracting and so on, getting the final solution, then plotting it. Today there are program packages which will do all this for you. All you have to do is really to enter the data for the problem. In some way I have to put down the differential equation problem with initial conditions and input, and then my package will take over, or the software will take over, and it will usually give me a nice graph on the oscilloscope or on the monitor, and I can take printouts, so I get plots. All that is okay, but that doesn't mean that I don't know anything as to what the sinusoidal function is, or what is exponential damping, or what is exponentially damped sinusoidal function, or what is the differential equation, or now what is the Laplace transformation. Programming packages don't mean that you don't have to know anything. It only means that what may take a long time, if you were to do it all by your own, for example, I can multiply two 10-digit numbers without using a calculator, but it will take me a long time. But if I have a ready-made program available, then essentially I have to enter the data, and then today the multiplication will be done in perhaps 1 microsecond or maybe 1 millisecond, faster than I can write down the number. But that doesn't mean that we don't learn anything about these things like differential equations and Laplace transforms or what have you, because all this, many ideas, design ideas, etc., make use of these ideas such as the Laplace transform and so on. In fact, the idea of a transfer function is essentially based on the concept or on the use of the Laplace transformation. So, you have to study the Laplace transformation. It is not something very difficult. Perhaps you already studied it in your mathematics courses and maybe in your circuit theory or network theory course. In control theory or control engineering course, certainly one has to know the Laplace transformation and how to use it. So, what is this Laplace transformation? How is it to be used? Why is it that it can be used for certain problems and why not for each and every problem? Now, Laplace of course was a mathematician. You can also call him a physicist because he was solving some problems in physics. He was interested in astronomy. He was interested in the propagation of heat. You come across his name in many places: Laplace's equation, Laplacian. One more thing that he contributed was not quite the Laplace transformation, but what was earlier called the Laplace integral. And his motivation was not solving differential equations as such, although he was interested in that problem. In fact, he was interested in the problem of motion of the planets, not just the sun and the earth. But when you have three bodies, the sun, the earth, and maybe Mars, which affects the movement of earth, and conversely the position of the earth or the movement of the earth affects the movement of Mars. So you have a three body problem. You can write down differential equations and then you have to solve them. He was also investigating many other areas, like he worked on the idea of probability theory and other related subjects. So he introduced this idea of using some kind of an integral to simplify certain problems that he was trying to solve. Subsequently, in the 20th century, which is over now, we are in the 21st century, when people were looking at differential equations in mechanics, they found that this Laplace integral was a useful tool. And so in the first decade of the 20th century, 1920s and so on, this method was developed and almost perfected, and therefore then it became known as the Laplace transformation or the Laplace transform method. Now, what is this method? As I said, this method involves Laplace's idea of using an integral. So obviously then you have to know what an integral is, but for an electrical engineer that's nothing to be afraid of. We already used integrals, but this integral is a little different. Suppose you were given some function, let's say it's our input function u of t, and as I told you, as control engineers, our action normally starts at some moment of time which we call the initial time and which we therefore label usually as 0, and we are interested in what happens thereafter. So we are interested in t greater than or equal to 0. So suppose we have some function specified u of t for t greater than or equal to 0. For example, ut may be sine t, cosine t, e raised to minus t, it may be t square, it may be 1, the constant function, whatnot. So I have a function u which is specified for values of t greater than or equal to 0, and greater than or equal to 0 literally means for all values greater than 0. So for t equal to not only 1 if t is seconds, 1 second, 10 seconds, but maybe 1 hour, 10 hours, 1 year, 10 years, million years, for all t. And this of course one represents diagrammatically as the t axis. I am trying to show here that I start at t equal to 0 and I am interested in what happens thereafter. So don't ask me what happens earlier. I am not interested in that. I don't know anything about it and I won't have to know anything about it. What is this, the state at t equal to 0? Tell me what it is, and then I may be able to find out what's going to happen thereafter. So we need to know a function for t greater than or equal to 0. Therefore the integral that one is talking about is not now just an integral, a definite integral with limits which are numbers like say 0 2, 3 and so on, the lower limit is 0, but the upper limit, one writes the symbol infinity, and so this is what is called an infinite integral, and therefore it is something which has to be handled carefully. It is not integral 0 to 1 ut dt, or since I mentioned the idea of a dummy variable, this definite integral is exactly the same number as integral 0 to 1 u tau d tau, and if some third person wants to introduce the symbol lambda, let him do so, integral 0 to 1 u lambda d lambda. All of these are one and the same number, and depending on what the function u is, I can calculate it, and you all know how to calculate it. So the lower limit is 0, the upper limit is 1 here. Here the lower limit is 0, the upper limit is the symbol infinity, which means I have to integrate the function or find the integral of the function not from 0 to some other time, but over the entire t axis going to the right of t equal to 0. That is for all future time. Now this of course is an idealization, because who knows anything about the future beyond maybe even a day or a year. But in mathematics we know, for example, we know the function sin t, and if t equal to 0, sin 0 is 0. If t is equal to 10 raised to 20, then I can find out what sin of 10 raised to 20 is. There is no bother. I am not saying this is 1 second and that is 10 raised to 20 seconds, because by the time we reach 10 raised to 20 seconds, maybe there will be another big bang or a big collapse or what not. That is different. Although I call it time, really what I mean here is a number t. So there is no harm in integrating over the entire interval, as it is said, from 0 all the way to infinity. But infinity is not a particular point on the t axis. It is not 0 to 10, 0 to 1 million or 0 to 1 billion. That is not infinity. So that is why we have to be careful with this symbol infinity. And there is one more complication. I take the integral from 0 to infinity, but not of ut, but of ut multiplied by a factor. Now this factor is something where many of you probably have already made mistakes when you solve problems involving the Laplace transform, or those who are learning it sometimes forget what this factor is, and when I ask students in examination, they are unable to remember it. Unfortunately, it is one of the things that you have to remember. This factor here is usually written as e, so the exponential function appears here, and the power or the exponent is written with a minus sign, minus, and there is one more symbol that makes the appearance, namely s into t dt. So it is not the function, but it is the function multiplied by an exponential function whose exponent is minus s. The product is integrated over the entire interval from 0 to infinity, that is over the entire right hand or positive time axis. Alright, in this e is familiar, but what is this s? What makes it a little difficult in the beginning is the fact that this s, we are told, is not simply perhaps a real number, but it could be a complex number. So it is not necessarily something like say 3 or minus 2 or what have you, but it may be minus 1 plus j, or it may be 2 plus j3. So this s then will stand for a complex number. But we know enough integration and Euler's formula is known, so I should be able to calculate this integral if I know what s is. And so here is one more homework problem for you. Find out the integral 0 to infinity of, I will choose ut equal to sin t, and I will give you the particular value of s so that you do not have to keep the symbol, but you can actually find out. So let us choose s as what we had earlier, say minus 1 plus j t dt. So calculate the integral of sin t multiplied by e raised to minus of minus 1 plus j into t, this product integrated from 0 to infinity. Calculate this number. Simply involves integration. The exponential with that jt, we know how to replace it by cosine and sine using Euler's formula. You will find that you will get an answer which will be not a real number, but which will be a complex number. And what will be the complex number? Well, since of course I know what it is, but of course I should also be careful, I should not make any mistakes. I know what the answer is going to be, and I'm just going to go through the steps of the answer, but after we have looked at this for a while, you will see what the answer is. So I see sine t, so then something I remember which looks like omega over s squared plus omega squared. In fact, we will see that this will be what is called the Laplace transform of sine omega t. The Laplace transform of sine omega t is omega divided by s squared plus omega square. One more thing that an electrical engineer and certainly a control engineer has to remember: not only Laplace transform what it is, but also Laplace transforms of some simple functions like the sine function here, sine omega t. Laplace transform is omega divided by s squared plus omega square. But what I have right now is not sine omega t, but I have sine t, which means I am considering a situation where omega is 1. So put omega equal to 1. So I will get 1 divided by s squared plus 1 squared. But now what I have in the integral is not minus st, but minus of minus 1 plus j. So in other words, now s is to be replaced by minus 1 plus j, and so I will get 1 divided by minus 1 plus j squared plus 1. Now of course this is some complex arithmetic that I can do, square, then put it in the rectangular form, convert to the polar form, or do rationalization or whatever, and I will get it as some real number plus j times some other real number. That is, I can get it finally in the rectangular form. Check that your integral value agrees with mine, that 1 over minus 1 plus j squared plus 1. Of course, you have to reduce this to the rectangular form and just check that it tallies. Okay, so we have to look at such an integral, but not just for one particular number s. We have to think of all kinds of all complex numbers, not just one. In fact, you normally do not evaluate this integral at all, although what I have done here, omega by s squared plus omega square, replace omega by 1 and replace s by something. This is something which we will have to do, as we will see, but I don't really have to calculate the integral. Why? Because somebody has done that for me already. You already have ready-made tables of Laplace transforms, and your control engineering book as well as your mathematics book, which talks about Laplace transformation, will have such a table. It may have a small table with maybe some 5 or 10 entries, but there are more exhaustive tables running over maybe 30 pages or even more, where all kinds of functions are listed with their Laplace transforms. People have spent that effort to save you the trouble, but still you have to know what it is. So this integral, then you can think of the integral, which is a complex number. For a particular s, there is a particular result. Now this result is then denoted by a symbol, which, following our convention in control, it is capital U of s. Why capital U? Because I have a small u, which means a function of time. Now this is something else that I am getting. And why u of s, or why do I write it and talk of it as u of s? Because for each number s, I will get one value of the integral. When I change s, for s equals minus 1 plus j, I will get one value. I can then change s to say 2 plus j3. Perhaps I will get another value.